very good morning and welcome to this course on the foundations of continuum mechanics. Today we will be going through the tutorial for week 9. So let us get started. The topics that we'll be covering today include stretch ratios, finite deformations, stretch and rotation tensors. We'll talk about the velocity gradient tensor and the rate of deformation and the spin tensors. And finally, we'll solve a couple of problems on the idea of compatibility. So let us get started with the first problem. So here's problem 1. Let us understand the problem first. So we are given a homogeneous deformation using this chi function, and then two vectors in the reference configuration are given to us, that is n1 and n2, and in part A we have to determine the stretch ratio in the direction of the vector n1. That is, for an element that is aligned with n1 hat direction in the reference configuration, we have to find out what is the stretch in that element as the deformation happens. Secondly, we have to determine the angle theta 1, 2 in the deformed configuration between two material line elements that were originally in the n1 and n2 directions. And thirdly, we have to determine the volume ratio of an infinitesimal material element under this deformation. So let's start with part A. So the stretch ratio along the direction n1 is given as the square root of n1 dotted with the Green's deformation tensor C dotted with n1, and C, the Green's deformation tensor, is defined as F transpose F. So remember, this is for finite deformations that we had discussed in this week. So in general, in finite deformations, we usually go for the Green's deformation tensor to get the stretches as well as the angle changes. So to find C, we need the deformation gradient tensor F, which is defined as xi comma a. So for this deformation that is given to us, we can easily find the deformation gradient tensor. So x1 comma 1 is a 1, x1 comma 2 is a -1, x1 comma 3 is a 1, and so on. So this is our deformation gradient tensor F, and using this we can find C, which comes out to be this tensor. So now let us find n1 dotted with this C dotted with an n1. Now n1 is given to us as this vector. So the stretch ratio in the n1 direction is simply the square root of this. So we can substitute n1 and C to find this. I'll leave it to you to do the matrix multiplication. And you'll find the stretch ratio in the n1 hat direction will come out to be square root of 2. So remember, stretch ratio is d small x upon d capital X, where d capital X vector upon d capital X magnitude is given as this n1 hat in this case. So we have found the stretch ratio for this element along n1 hat direction to be square root 2. So the element is getting elongated. So in part B, we have to find out what happens to the angle between two elements, n1 hat and n2 hat, after deformation. So the two vectors are given to us, so we already know the angle between them. We have to find out what happens to the angle between them as the deformation happens. So again, for the finite deformations, we had defined the cosine of the angle between two elements as this, and there's a quick check you can do. You can put n1 equal to n2 here, and you will see that the cosine of the angle between them is going to be 0. So and n dot c dot n is simply lambda squared, so this comes out to be 1. So that's a quick check to make sure that we have written the right formula. So given that we know C and N1 and N2 are also known, we just found out lambda N1 and lambda N2 can be found out as N2 dot C dot N2 square root. And since N2 is simply I2, so this comes out to be square root of C22. So if we substitute all these, we will get the cosine of theta as 1 upon root 3. And then we can find theta as the cosine inverse of 1 upon root 3, which in degrees is 54.7 degrees. So this is the angle between N1 and N2 in the deformed configuration. And finally, in part C, we have to find the volume ratio for an infinitesimal element. So the volume ratio for an infinitesimal element is defined as the volume of that infinitesimal element in the deformed configuration to its volume in the undeformed configuration. And for finite deformations, this is given as the square root of the third invariant of C. And the third invariant of C is nothing but the determinant of C. Well, the determinant of C is 16, so this becomes square root of 16, which is 4. So infinitesimal volumes become 4 times larger in the deformed configuration for this deformation. So this completes problem 1. Let us move to the next problem. So here's the second problem, and we can see a deformation is given to us with alpha, beta, and mu being constants. So in the first part, we have to find the magnitudes and directions of the principal stretches. Again, this is a finite deformation, and we also know that the tensor C, the Green's deformation tensor, has the information about the stretches. In fact, the diagonal components of C have the information about the stretch in that direction. So using that, we can find the principal stretches, that is the stretches along the principal directions of C. In the second part, we have to find the matrix representation of the rotation tensor R. So recall that we had discussed about the polar decomposition where finite deformations are decomposed into a symmetric stretch tensor and an orthogonal rotation tensor. So here we have to find that orthogonal rotation tensor R. And additionally, associated with this rotation tensor R, there will be a vector around which the rotation is happening. So we have to find that rotation vector around which the rotation is happening in this case. So let us solve the problem. So in polar decomposition, we mentioned that the deformation gradient tensor F is decomposed into a product of a rotation tensor, which is an orthogonal tensor, and a symmetric tensor, which is called the symmetric stretch. So here this R is responsible for rigid body rotation of the object, and U, the symmetric stretch tensor, is responsible for stretching of the elements, and the stretching can also result in rotation, but that is not a rigid body rotation. This is the rotation of individual elements which results because of a stretch. And we had discussed about this idea of stretch induced rotation. Now since U has the information about stretch, so if we have to find the principal stretches, that means we have to find the principal values of this tensor U. So we had defined U square as C or U dot U as C, and that is the reason we can find the principal values and direction for either C or U, because the principal directions of both are the same, and the principal values of C are simply squares of the principal values of U. But since U denotes the stretch in the body, so the principal stretches will be denoted by the eigenvalues of U, not C. So to get C, we need to find F, because C is F transpose F, and F can be found easily from this deformation that's given to us. So from this we find that f is equal to this tensor, and this is the c that we get from this f. And interestingly, we see that this is already diagonalized. So what that means is that in the coordinate system that we are working in, the coordinate directions are already the principal directions of C. And the principal values of C are these. And the stretch ratio in, let's say, the I1 hat direction was square root I1 dot C dot I1, which is nothing but C11. So in this case, this is C1, the square root of that. So therefore, I can find the principal stretches, that is lambda 1, which basically is lambda along principal directions of C, as root 2 alpha, root 2 beta, and mu. And the principal directions corresponding to these principal stretches are simply I1, I2, and I3. And these actually are the eigenvalues of our symmetric stretch tensor U. So this completes part 1. Let's move on to the next part. Now in part B, we have to find the rotation matrix R, and we define the polar decomposition as F equals R times U. So we already have F, and we have found out U as well, which in this case is a diagonal matrix. All we have to do is we have to find R as F times U inverse. Since this is the form of U, finding U inverse is very easy, which comes out to be this. So basically, we get the reciprocal of the diagonals in the U inverse for a diagonal matrix. So when we substitute these, we get the R, or the rotation matrix, as this. So this completes part 2. Now part C is interesting, where we have to find the vector around which the rotation is happening. Now remember, when we talk about rotation, rotation happens around an axis. So in this case, we have to find the axis of rotation. Now the way rotation works is that if you have a vector n hat and you apply a rotation to it, so you multiply this r with an n hat, and that gives you the rotated vector. And that is the whole idea of linear transformations that we had discussed in the topic on tensor transformations. So when you transform a vector, you basically multiply that by a matrix associated with the transformation. Now in this case, if n hat is the axis of rotation, let's say this, and when you rotate around this axis, this vector does not change at all. So basically, we get an n hat back if n hat is actually the axis of rotation associated with r. For any other vector, it will get rotated. So if I write this in the matrix form, what I get is, so this is the matrix form for the above equation, and we'll call this 1. And along with this, we can use the condition that n is a unit vector. What that means is that n1 squared plus n2 squared plus n3 squared is equal to a 1. And let's call this equation 2. So using these 1 and 2 equations, we will get the axis of rotation as simply I3 hat. So basically the rotation is happening along the I3 hat direction, or capital X3 direction. So let's move on to the third problem now. So in this third problem, a velocity field is given to us in the spatial coordinates as this, and we are interested to evaluate different quantities at the spatial point 1, -1, 0 and at time t equals 1. So in part A, we have to find the rate of deformation and the vorticity tensors. In part B, we have to find the rate of stretching per unit stretch along a certain direction n hat, and this requires the use of the rate of deformation d, and in part C we have to find the maximum stretch per unit stretch, which will be associated with the eigen values of d, and finally we have to find the maximum shear strain rate. So let us solve the problem. So in the first part we have to find the rate of deformation and the vorticity tensors. So basically we have to find first the velocity gradient tensor, which for this velocity field can be found out as this tensor, and the rate of deformation tensor dij is simply the symmetric part of Lij, and the spin tensor W is the skew symmetric part of Lij. Now since we are provided with a point and a time, so rather than keeping d and w expressions general in axis and time, we will substitute the value for the point coordinates and time to simplify the calculations. So for this point at time t equal to 1, we get the rate of deformation tensor d as this, and the vorticity or the spin tensor as this. And you can check that d is symmetric and w is skew symmetric. Now let us move to part B. In part B, we have to find the rate of stretching per unit stretch in this n hat direction. Now the rate of stretching per unit stretch, that is lambda dot upon lambda, was defined as n hat dot d dot n hat. So since we already have found out d and n hat is given to us, we can substitute these and get the rate of stretch per unit stretch. And this rate of stretch per unit stretch is also given as the rate of elongation per unit length in the spatial coordinates. And this rate of stretch per unit stretch is going to be 4/3. Now in part C, we have to find the maximum stretch rate per unit stretch. So in part B, we found out lambda dot upon lambda for a given n hat, that is for a line element in a given n hat direction. But now we have to find the maximum value of this and also the direction in which this maximum stretch rate per unit stretch occurs. Since dx dot upon dx is given as n dot d dot n, and if I substitute, let us say n hat equal to E1, then what I get is I get the dx dot upon dx along the element in the E1 hat direction, which is the diagonal component d11 of the rate of deformation tensor. And if I rotate my coordinate system in such a way that my E1 hat, the new one, coincides with that n hat for which I get the maximum stretch rate, then my D11 will be the maximum rate of stretch per unit stretch. And for a symmetric matrix, we know that it is the eigenvalues or the principal values which denote the maximum values of the diagonal or the normal components. So if I draw the Mohr circle for this case with the three eigenvalues written as d1, d2 and d3, then d1 denotes the maximum value for the normal component. So this basically corresponds to the maximum value for dx dot upon dx in this case, because dx dot upon dx corresponds to the diagonal component if my coordinate axes are aligned with the vector of interest. So if I find the principal values of D, they come out to be -1, 1, and 2. So the dn max is 2, which is the maximum value for the rate of stretch per unit stretch. And since we also have to find the direction in which this occurs, actually if you look at D, we see that this value 2 is along the E2 direction and there are no components here and here. So this basically is one of the eigenvalues as we have noticed in this case, and the direction associated with this value D2 is simply the E2 direction. The direction associated with the maximum value for the rate of stretch per unit stretch is E2 hat. Now in part D, we have to find the maximum shear strain rate. Now strain rate is nothing but the rate of deformation, and the shearing is quantified using this equation where theta dot is the change in right angle between two perpendicular vectors n1 hat and n2 hat. So basically if you take two perpendicular vectors n1 and n2 and then you notice how the angle between these is changing with time, that is theta dot. So in this formulation we have a minus theta dot by 2. So this is basically half of the rate of decrease of the angle theta that initially is a right angle with time. So we have to find the maximum for this rate of decrease by 2. And of course, this will occur for a selected choice of these n1 and n2. There could be some n1 and n2s where there will be no rate of shear, that is the angle between them will not be changing, and there would be some n1 and n2 for which we'll have the maximum rate of decrease. So we have to find that situation where the rate of decrease is the maximum. And for this, we use the idea of a Mohr circle. So before I show you the Mohr circle formulation for rate of strain or the rate of deformation tensor, which is also a symmetric tensor by the way, we will first go back to our initial discussion on Mohr circles, which was in stresses, and I will show you an analogy of that situation with the rate of deformation that we have in this case. So in case of stresses, we had a cutting plane which was designated by a normal n hat, and on this plane we had traction Tn hat, which was decomposed into a component along n hat, which we called sigma n, and a component perpendicular to n hat in the plane which is formed by n hat and Tn hat, and this was called sigma s. And it is these sigma n and sigma s's that were plotted on the stress plane. So sigma n was given as traction dot n, which using the Cauchy stress tensor can be written as sigma dot n dotted with an n, which actually becomes n dot sigma dot n. And then sigma s, the other coordinate in the stress plane, was given as a direction p hat. So this was given as the traction vector dotted with p hat. So this becomes sigma dot n dotted with the p hat, so which can be written as p dot sigma dot n hat. So I'll call these A and B. So this was in stress. Now in strains, we have dx dot upon dx, which we call the rate of stretch per unit stretch, as n dot d dot n, and the rate of decrease of the angle upon 2 as p dot d dot n hat, where p is our n1 and n hat is the n2. and this I'll call A1, and this I'll call B1. Let's look at this n dot sigma dot n and n dot d dot n. So we see that they are very analogous. And similarly, if I look at equation B, I have a p dot sigma dot n and I have a p dot d dot n. So we can clearly see that there is an analogy. And in the Mohr circle for the stresses, in the stress plane, our abscissa was sigma n and the ordinate was sigma s. So by that same logic, in our strain plane, our abscissa will be the quantity lambda dot upon lambda, and the ordinate will be the quantity minus theta dot upon 2. So these are the three Mohr's circles for the case of rate of deformation d, and just like we had in stresses, these values are d1, that's the largest principal value of d, d2 and d3, which is the smallest principal value of d. And this point here corresponds to the maximum value of minus theta dot upon 2. And this is exactly what we had to find in this case. So we can write minus theta dot upon 2 maximum is the radius of this largest circle, which basically is d1 minus d3 upon 2. And for this case, d1 was found out to be 2 and d3 was actually negative. So in the figure above, the axes are not correct because I've drawn all the principal values positive upon 2. So this comes out to be 3 by 2, which is 1.5. So this completes problem 3. Now additionally, just some clarification on the Mohr's circles for strains or rate of strain, that is the rate of deformation. This direction p hat in the case of stress is unique in the sense that if you choose an n hat, which basically denotes your cutting plane, then Tn hat is dependent on the stress tensor sigma, because Tn hat is sigma dot n. And then our p hat automatically is the direction which is in the plane of n hat and traction. So if I choose an n hat, then my p hat is already decided. However, if we talk about strains, then we have to choose two directions. One is an n hat and the other is a p hat. Of course, they're perpendicular, but the choice is independent. So if I make a choice of n hat, then I have infinite number of choices for p hat, because p hat is a vector perpendicular to n hat. So there's a whole plane, which basically in the stress is this plane, in which I can choose my p hats. And since minus theta dot upon 2, which is one of the coordinates in this strain plane, is dependent upon p hat, so as we change p hat, we will see that the dot product between p hat and the vector formed by d dot n will keep changing. And actually, if you think about it, then for this choice of p hat, which is in the plane formed by d dot n hat, which is similar to a traction vector in stresses, and n hat, that dot product will be the maximum in this case. But as I rotate my p hat in the plane perpendicular to n hat, my values of p dot d dot n will vary. So let's draw it. So we have an n hat, which is some direction, and this is a plane in which I'll have to find a p hat, and this vector is d dot n hat. So if I choose an arbitrary p hat like this, and I choose an angle phi here, which is an angle made from the axis along which this p hat special lies, which is similar to what we had in stress, then what we see is that the component of d dot n along p hat special is the maximum. And as my p hat rotates and I take it to a condition where it's normal to p special, then I'll see that this quantity dotted with this p hat will be 0. So that basically means that in the strain plane, where my lambda dot upon lambda purely depends on n hat, so let's say we have chosen n hat, so we get some coordinate for lambda dot upon lambda, and then for this p hat special we get some value for minus theta dot upon 2 as well, that's the ordinate. But as I rotate my p hat special, what happens is that this value starts going down to 0, and then it becomes negative as my p hat starts going here. It goes all the way down. So for a given value of lambda dot upon lambda, I have lots of values for minus theta dot upon 2. So each n hat choice in this Mohr circle for strains gives us a whole line. So basically, if you think in terms of Mohr circles, then the region inside the circles is also feasible. But since we are interested in the maximum values for the shear strain rates, so what we do is we stay with this P special. So that gives us the maximum shear strain rate for a given choice of n hat. And amongst these, in this problem, we found out the overall global maximum minus theta dot by 2. But one must understand that there is a subtle difference between the Moore's circles for strain or strain rates and the Moore's circles for stresses. I'll just summarize that the region inside the Moore circles is also feasible, and this is because the choice of p hat is not unique for a given choice of n hat in strains. So now let us discuss problem 4. So we have a velocity field that's given like this, and it's given that it corresponds to rigid body rotation, although it's not required because we can find the velocity gradient tensor and identify ourselves whether it is rigid body rotation or not, but that's already given. And we have to determine the axis of spin, that is for the vorticity tensor wij, we have to find the vorticity vector omega. So first let us find Lij, which comes to be this, and we can clearly see that this is skew symmetric. So this is actually equal to wij, that's already given, and d is therefore 0. So for this rigid body rotation case, we can define a dual vector omega I as half epsilon ijk times the spin tensor wkj. So if I put I equal to 1, I get omega 1 as half epsilon 1jk wkj, and this I'll expand over j and k because they are dummy indices. So this becomes half of epsilon 1. Now I'll take j equal to 2 and k equal to 3 because the only two possible values for j and k is j equal to 2, k equal to 3, and j equals 3, k equals 2. Because for any other combinations, epsilon will turn out to be a 0. So this is W32 plus here we have WKJ, this is W23. And let's expand this. So epsilon 123 is a 1, and W32, which is L32 in this case, is this component. So that's a 1 as well, plus epsilon 132 is a minus 1, and W23 is minus 1. So this is a minus 1 as well. So this becomes half of 1 plus 1, 2, which is ultimately a 1. So the first component of the vorticity vector omega is a 1. And similarly, I'll leave it to you to find omega 2 as 1.5 and omega 3 as a 3. So the omega vector therefore is E1 plus 3 by 2 E2 plus 3 times E3. So this completes problem 4. Now this is problem 5, and what's given is that the curl of a tensor A is defined as this, and a tensor C is defined as the curl of epsilon, where epsilon is our infinitesimal strain tensor, or it could be any symmetric tensor. And in part A, we have to show that in the index form, PL component of C is given as this. And this problem is actually coming from compatibility, where while deriving the compatibility equations, we had mentioned that the curl of epsilon is 0, and I had mentioned in the lectures that you have to show it yourself. So we are solving that as a tutorial now. And in part B, we have to show that C is symmetric, because from this symmetric property of C, we had shown that there were 6 equations of compatibility, not 9. So let us solve the problem. So we'll call the curl of epsilon as S, and this quantity C is now the curl of S. So the PL component is the curl of SPL component, and this turns out to be epsilon P, let's use the indices Q and R, and then S, L, R, comma, Q. And this we can see from the definition here. And now since S is the curl of epsilon, so we are interested to find the LR component of S. So the LR component of S is the LR component of curl of epsilon, which turns out to be the permutation symbol epsilon LJK times a strain RK comma J, like this. So let's substitute that here. So this becomes, I'll use the word epsilon for permutation symbol and strain for the strain. Epsilon PQR times epsilon LJK times strain RK comma JQ. And this is exactly what we had to show. So this completes the part A. Now we move on to part B, where we have to show that C is symmetric. That is, we have to show that CPL is CLP. So let us write CLP using the expression for CPL. So this becomes epsilon LQR epsilon PJK and then strain RK comma JQ. And I'll write CPL as well, just so that we know what we're trying to show. So now we'll do some index manipulation, because I want to make this as the same as this. So the indices J and K have to be made Q and R, and the first epsilon in the second has to become the second epsilon in the first. So I have to replace Q and R with a J and a K. And since all these are repeated indices, I can do that. So the manipulation I do here, I'll write that in red, that I'll make a Q, a J, I'll make an R, a K, and the existing J will be made a Q, and the existing K will be made an R. So let's do that. So this is epsilon L, and then a Q becomes a J, R becomes a K, and in the second epsilon we have epsilon P, and then a J becomes a Q, and a K becomes an R. So in the strain, the R becomes a K, K becomes an R, J becomes a Q, and Q becomes a J. So this still is CLP, because we have not touched the free indices. And now if I compare this to CPL, I can see that epsilon PQR is there and epsilon LJK is there. But now if I compare these terms, they look slightly different. But that's okay because strain is symmetric tensor. So I can write strain KR as strain RK, and since the mixed derivatives can also be commuted, so I can write strain RK comma JQ, and this now becomes exactly the same as CPL. So we have shown that CLP is CPL, so therefore C is symmetric. And that completes the solution. And now we come to the last problem for today's tutorial, which says that we have to show that the curl of the deformation gradient tensor is 0, which basically is the compatibility condition for finite deformations. Because this provides a relationship between the different terms in the deformation gradient tensor, telling us that the 9 components of f are not all independent. There is some relationship between them. So let's solve the problem. We'll write the LHS in the initial notation. So this becomes epsilon ABC f I c comma b. So this is the curl of a tensor, and FIC is defined as small x I comma c. So this becomes epsilon ABC x I comma cb, and this I can write as xi comma bc. So if the x field is smooth, then this is true, and this is the key step here, going from here to here. And now we do some index manipulation. So b becomes a c and c becomes a b. So this becomes epsilon acb, and using the property of epsilon, I can write this as negative of epsilon abc, and here you have xi comma cb. But it is the LHS that is here. So this is minus of LHS. So what we have shown is that LHS twice of that is 0. This implies that the curl of f is a 0. This completes the solution. So this now brings us to the end of this module, and we'll meet next week with a new module on balance laws. Thank you very much, and I'll see you in the next lecture.